Did you know that there's an absolute hottest temperature? Absolute hot is actually the temperature above which our physics stops working, and we have no way to like describe or understand such a temperature. This temperature is like so hot that basically above this, you're in kind of uncharted physical territory. We have like no physics to describe it. So absolute hot is 100 million degrees, 5 millions, like a 1.5 with 32 zeros after it. It's 1 times 10 to the 32 Kelvin.
Professor Hamden, my response is not a critique. It's really an honest question. You argue that the absolute hottest hot temperature that we could possibly reach is about 1.5 with 32 zeros after it. I assume this is based off of Wien's law for blackbody radiation. And your argument then would be that the photons emitted are so energetic and so small that they would then violate all the physics that we understand things. I would have said that the absolute hottest temperature you could possibly reach would be about 3 trillion Kelvin, or 3 with 12 zeros after it. And I want to know what you think about that. In material science, we define the thermal energy of something based on how fast atoms are bouncing around inside of an object. And so using this equation, 3/2 kT, we would find the thermal energy of something, where K is Boltzmann's constant. This is an average energy of atoms moving within an object. And so we can relate that to the kinetic energy of the atoms within that same object. And kinetic energy is just telling us how fast things are moving, squared. Using these, we can calculate that the average speed of the molecules in this room are moving at about 500 meters per second, or 1100 miles per hour. So I'm currently being hit in the face with nitrogen molecules going about 1100 miles per hour. But they're so tiny, it's not so bad. I can easily exchange that energy with the other atoms around me. So if I use these same equations to calculate the absolute hottest hot temperature that I could possibly have, I would say that the fastest they could move would be the speed of light, or 30 billion meters per second. And that gives me 3.5 trillion Kelvin. Now, I know I'm using a classical definition of atoms, so I could be off by a few zeros. Even so, I would think that relativity would get in the way before Planck's does. Thanks for pondering with me.